guess I'll just, yeah. Yeah. Yeah, I'm sure you will. It's still, yeah.
Still early.
Still early.
The Multidisciplinary Drifting Observatory for the Study of Object
Yeah,
Clocks.
so that's still on my list.
Really long.
There's too much ambient light frequency, and then
Yeah, it's funny, like, I feel the need to say what it is sometimes, like, but if I'm really that's the whole, that's like half of the
Good morning. I want to get started with our first thing on the program, an update from the Mosaic project that's up in the Arctic. And we have three scientists here with us today, Sally McFarland, Stephanie Arndt, and Melinda Webster. Already got her name wrong once. But we also have two people joining us from the Polar Stern in the ice pack. And I'm going to turn it over to Katie Weeman to introduce them.
Thanks, Liza. Hi, I'm Katie Weeman. I'm from the Cooperative Institute for Research in Environmental Sciences. And thanks for coming to A Year on the Ice, Mosaic at 3 months. Mosaic is the multidisciplinary drifting observatory for the study of Arctic climate. It's an international research expedition to study all aspects of the Arctic system, from the ice to the sea to the sky. Germany's Alfred Wegener Institute is leading the expedition with key support from the Cooperative Institute for Research in Environmental Sciences, which is a partnership of the University of Colorado Boulder and NOAA. It's a huge international collaboration, and U.S. participation is primarily supported by the National Science Foundation, which is contributing roughly $24 million to the project, making it their largest Arctic research initiative to date. The U.S. Department of Energy is also highly invested in the mission, funding nearly $10 million. Mosaic seeks to understand our changing Arctic, so we also want to point out that this aligns very well with the broad science goals and findings of NOAA's Arctic Report Card. That press conference will be today at 11. And now to introduce our panelists, we'll start with those who are here with us via radio phone, satellite iridium phone from the Polar Stern. So we have Marcus Rex from the Alfred Wegener Institute. He's the Mosaic Project and Expedition Lead. We have Matthew Shoup from Ceres and NOAA. He's the Mosaic Co-Lead. And then for our in-person panelists, we have Sally McFarland from the U.S. Department of Energy, Atmospheric Radiation Measurement Climate Research Facility. She's the Program Manager for the ARM User Facility. Then we have Stephanie Arndt from the Alfred Wegener Institute. She's a sea ice scientist who will be going on leg 3 of the expedition. And then we have Melinda Webster from the University of Alaska Fairbanks. She is a sea ice scientist going on leg 5 of the expedition. So with that, I think I'm going to turn it over. Are we still connected? Matthew and Marcus, can you hear me? Uh-oh. Oh, crap. Okay. Well, stand by.
Research for Polar Stern. This is Communication Officer Frank. Good evening.
Hello, I think we got disconnected. Are Matthew and Marcus still there?
Hi, Katie. Everybody's still here. Katie?
Talk to the next mic. All right. Thanks, Amy. So we just introduced the panelists, so if Marcus wants to start with his talk, we can start with that.
Yeah, more than happy to do that. Greetings from Polar Stern here in the Central Arctic, from the vast emptiness around us of the sea ice and the darkness of the polar night. Right now we are at 87 degrees north, so we are on course due north, 121 degrees east, and we are locked into the ice, and we are drifting with the natural drift of the ice. We are a pretty isolated outpost of mankind up here at the northern end of our planet, with the next human soul about 1,000 kilometers away, and we are working on the ice every day at temperatures which are often around minus 30 degrees Celsius and sometimes during fierce storms. Mosaic is the largest Arctic research expedition ever, with one full year operation of our flagship, the Polarstern, in the Central Arctic, close to the North Pole. And during this year, Polarstern is supported by our 4 partner icebreakers from Russia, China, and Sweden. And Mosaic is a truly international effort, with key contributions from more than 70 scientific institutions from 19 nations. A total of about 600 people will operate in the Central Arctic as part of the expedition in different phases, and the overall budget of the expedition is 140 million euros. So why are we doing all this? The Arctic is the epicenter of global warming. We are really in the center of action here. The warming rates are far above those in any other part of the world. And we do not understand this Arctic climate system very well. It's the reason where our climate models have their largest uncertainties, and these uncertainties are actually huge for the Arctic. We have never been here with a modern icebreaker in winter, and we lack even the most fundamental data from the complex climate processes that take place in winter in the Central Arctic. We have been here with icebreakers in summer, but never really were able to cover the winter season. And we are...
Oh, no. Did we officially lose connection? Okay. Well. Almost worked perfectly. So with this, I'll say that we do have pre-recorded audio of both Marcus and Matthew's talk here that we were going to play in case it didn't connect at all. So if you're interested in that, feel free to find me after, and I'm happy to email that to you. Okay. Sorry, Marcus, I think we lost just the last couple seconds of your talk. Do you want to say just the last few sentences that you were going to say?
Yes, I just continue where I stopped. And I was just about to say that when we arrived here, a few months ago, we came to the Arctic in late September. We found that the ice was thin and eroded, which was a result of the unusually warm summer up here in the Arctic this year. And nevertheless, we found an ice flow that is suited as a basis for our large research camp here on the ice, which we have set up next to our vessel. The flow is not perfect. It is thin and keeps breaking as all the other flows here in the new Arctic. But it has a thicker and stronger core that provides some stability, at least for us. And we constantly adapt our setup to the deformations of the ice and to the new cracks and ridges that form on a near daily basis. We have to interrupt our work when curious polar bears pass by as well, so we cannot measure every day. But our comprehensive measurement program is in full swing. We are collecting data to better understand the complex coupling between the atmosphere, the sea ice, the ocean, the ecosystem, and the biogeochemistry of the Central Arctic. And very persistently, we will keep this program up and running for the full year, no matter which obstacles the Arctic will throw at us. It is our mission to provide a robust scientific basis for the important decisions our societies have to make to mitigate climate change. And with that, I wish you a very successful conference over there in San Francisco.
Thank you. Matthew?
Okay, hi, this is Matthew Shoup, also coming from Polar Stern, and very happy to speak with you. I want to say a few words about the science and the scientific design of this fantastic project, Mosaic. We've been on the ice today and every day so far here, and indeed it's the ice that's really the centerpiece of our experimental design. The ice is so important here as an integrator of energy, a substrate for biological activities, a dynamic material itself, and really one of the key aspects of the changing Arctic system. So we'll follow this chunk of ice, this region of ice, for a full year to understand all the processes it undergoes, the causes of its changes, and the implications those have on the rest of the Arctic system. Our starting point is an interesting one with this really relatively thin and weak ice. It's posing a challenge for us, of course, with all the dynamics kind of happening right underneath our feet. But really, this operational challenge is also a huge scientific opportunity for us to understand current Arctic conditions, because these are Arctic conditions right now. And we have this multi-scale design to accomplish our science objectives out here. First, sitting here on board the ship is a tremendous suite of instruments. It's really packed full of great science. Ground-based remote sensors probing the atmosphere and clouds, laboratories for processing samples of water and ice, balloons flying up into the air, and so much more, just really packed onto the ship. It's really amazing how much we have on board. Nearby the ship, we have our ice camp with different cities. We have places called Met City and Ocean City, Remote City, and others, where we make measurements that need to be away from the ship, that need to be away from the influences the ship might have on those measurements. So Met City, for example, of course has a lot of meteorological measurements. So we're looking there with towers and other sensors at precipitation and radiation and turbulence and a lot of other atmospheric processes. But we also have sensors there from other teams from Mosaic. We have, ocean turbulence measurements, ice mass balance measurements, snow depth arrays, gas flux measurements, and even a fish camera. So it's all these pieces working together to help us understand how the complex, coupled Arctic system functions. Surrounding our drifting ice camp here, out at scales of tens of kilometers around us, is our distributed network. This was set up initially by our partner vessel, the Fedorov, and we now harvest data from that distributed network to understand the context for our measurements here on Polar Stern, and to really understand the spatial variability across this region. And that variability is so important for us to capture and ultimately represent in models. We've had some excitement, of course, keeping that network alive. The ice dynamics sometimes crushing some of the sensors, polar bear visits knocking out some stations. But in the end, the stations are alive. I think we're very functional. We have a really nice drifting constellation, and that will be in action for a full year. And that's a really important part of Mosaic. This full year will allow us to look at the processes as they play out in different seasons, to study the key interseasonal interactions and feedbacks. And so we've been here for about 2 months now, and we really look forward to the next 10 months to carry out this full annual cycle. All these factors coming together, the full year, the interdisciplinary nature of the project, the distributed measurements with sea ice as the focal point, these all collectively make Mosaic a really unique and distinctive opportunity to study the rapidly changing Arctic system. So here we are. We've set up tons of instruments on Polar Stern. We've built installations on ice, deployed many autonomous systems across a large domain, and we've joined forces across disciplines and across national boundaries to address pressing science questions that will help us better understand, model, and manage the changing Arctic and its impacts on the global system. So with that, I'll thank you for listening.
Great, thank you so much. And I will turn it over to Sally.
Okay, thank you. So I'm Sally McFarlane. I'm the program manager for the ARM user facility at the U.S. Department of Energy. Mosaic is a very exciting science expedition and a fantastic example of international collaboration for scientific research. While it's led by Germany's Alfred Wegener Institute, the campaign currently includes contributions from 20 countries. The U.S. is one of the largest contributors to Mosaic, with significant support from the National Science Foundation, the Department of Energy, NOAA, and NASA. Mosaic was specifically called out as an example of international scientific cooperation on Arctic research by the joint statement from the Second Arctic Science Ministerial in 2018, which noted that participation in Mosaic and other activities associated with the years of polar prediction was expected to increase predictive capabilities for Arctic weather and climate and their connections with the global system. The Department of Energy is playing a critical role in the Mosaic campaign through our Atmospheric Radiation Measurement, or ARM, user facility, and support of 2 early career researchers who are studying Arctic aerosols. ARM is deploying over 50 instruments to characterize atmospheric structure, aerosol and cloud properties, and their interactions with the surface. The deployment of the ARM instrumentation was actually based on a science proposal by Matt Shoup, who we heard from earlier, and members of his science team will be on board the Polar Stern working with the ARM data as well as many of the other observations throughout the cruise. The ARM instruments were installed on the Polar Stern by a crew of over 10 scientists and technicians and who participated in leg 1 of the campaign. And ARM will have 3 staff on board the Polar Stern throughout the cruise to maintain the instruments. They'll also be monitored by US scientists remotely. The atmospheric measurements taken by ARM and many of the other participants in Mosaic are expected to provide critical data about Arctic atmospheric processes and how the atmosphere and surface interact through the annual cycle in the deep Arctic. For example, little is known about some important questions such as the energy budget of the first-year sea ice, the annual cycle of Central Arctic aerosol concentrations, the spatial organization of cloud systems relative to the sea ice heterogeneity, and winter boundary layer evolution in the Central Arctic. We expect that the observations from Mosaic will be used to evaluate and improve processes in weather and climate models. A key aspect of Mosaic that's already been mentioned is that scientists are not just observing one aspect of the Arctic system, but they're making observations of the atmosphere, ocean, and sea ice, and these data will all be used together to improve the accuracy of these coupled Arctic processes and models. Data from the campaign is already beginning to be available to the Mosaic science team. Due to the limited bandwidth available on the ship, we've seen a little bit of that today. Most of the data that ARM is collecting will actually come back to our data center via disk. And we actually received our first data back from the crew who participated in the installation in leg 1A, and they brought disks back with them on the Fedorov. More disks will be sent back every time there's a resupply of the Polar Stern. However, in order to be able to monitor the instruments and so that the broader science team can get a picture of what is happening during Mosaic, we create these quick looks or plots of our instrument data that can be sent back over the satellite link daily. So this figure shows an example from one of our LiDAR instruments. The LiDAR basically sends a laser beam up into the atmosphere that scatters off cloud and aerosol particles in the atmosphere. And the amount of light scattered back and the characteristics of that light tells you about those particles. So we're looking forward to much more data like this from Mosaic. Thank you.
Good morning. My name is Stephanie Arndt. I'm from the Alfred Wegener Institute in Bremerhaven, and I will be the team lead of the ICE team on Leg 3 during Mosaic. In addition to my responsibility as the team lead, I was part of the organizational team of the snow work on board Polar Stern during Mosaic, which means that snow will be a crucial, or is a crucial element when talking about sea ice and the interaction between atmosphere, sea ice, and ocean. And therefore, we had a big work topic on snow, also during Mosaic. And therefore, I want to put my short presentation here in the perspective of a snowflake when looking onto Mosaic. So as part of this snow work, we were of course then also contributing to the overall planning before Mosaic started, where we set up, or where we had just in our minds an idea how should the flow look like with all the different cities that Matthew just mentioned beforehand. And we had this imagination on how this should look like, but of course in the end, in the setup phase, starting in beginning of October this year, when they reached their final Mosaic flow, they needed to adapt that plan to reality, But also this adaptation was then, of course, still not the final, as the entire system around polar ocean is pretty dynamic, and therefore they have to adapt their science and their work on the flow more or less on a daily basis. And then in mid of November, they experienced a big storm where the flow broke apart, and big part of the entire scientific stuff on the flow had to be kind of reassembled. Everything is working still, and we are still happy to collect all the data, but that just shows that even though we did a lot of preparation and planning beforehand, we must be always that flexible to adapt ourselves to reality and to the weather conditions and sea ice conditions. And therefore also going on board as a team lead of the ice team, it's really tough in terms of preparation, because we can't prepare ourselves for anything except for all those dynamics and changes all the time. However, seeing myself as a researcher on snow, in this entire process, all over the period of Mosaic, we want to study snow processes and properties in the Arctic sea ice climate system, and how does snow changes over different parts of sea ice, on first sea ice, on multi-year ice, on those ridges, on those new formed leads, which they just experience again and again and again in the last couple of weeks and months. In addition, those surface properties, and especially snow properties, we do not only want to study on this on one point in time, but of course over the whole sea ice, over the whole drift of the sea ice and of Mosaic, and therefore we really want to tackle the interannual variability in those, the annual variability in those snow properties and processes. All over, this seasonal change in snow properties is not only important for sea ice, but it's really of big importance for energy fluxes from the atmosphere to the oceans through the sea ice, in combination with the biogeochemical fluxes and all that stuff. So therefore, we do really see snow as kind of the connecting element between all those interdisciplinary disciplines we see on board during Mosaic, and to therefore see here the big need, and we do see the big need on studying those snow processes, and I'm really curious to see what is going to happen on Lake 3, especially when the sun will come back with our lake.
Hello, my name is Melinda Webster. I'm a sea ice geophysicist at the University of Alaska Fairbanks, and I'll be joining the Mosaic expedition on Lake 5, so that will be from June to August. And this period is the summer melt period, and it is the most rapid transformation of the sea ice cover of any point throughout the annual cycle. It goes from this beautiful, cold, snow-covered environment that Steffi was talking about to something where things start melting and these puddles of meltwater start forming on its surface. These are deep turquoise colors of meltwater pulled into the depressions of the sea ice surface. And although they're aesthetically beautiful, they're not as reflective as the surrounding sea ice. So they actually absorb more sunlight and warm up and actually melt the sea ice much more quickly. By the time that it's July on Lake 5, it's going to look more like that third image up there, where you'll have very melted, degraded sea ice. It's in a highly advanced state of melt. And this is becoming a more and more common view when you go up to the Arctic, because the Arctic sea ice cover is becoming more seasonal. By the time that I leave the polar stern in mid-August, there is a possibility that the ice at the Mosaic site could be completely melted. We really don't know. This is dependent on the weather conditions, how many storms occur, how much snowfall occurs, and also what's the state of the sea ice cover and where has the polar stern drifted to, which in part will determine how much warm water the sea ice is exposed to. Now, the summer melt season is really exciting in terms of all these rapid changes, but what I'm interested in for my project is looking at this in the context of what satellites see. So the summer melt period is notoriously difficult for satellites to measure sea ice properties accurately. And what I'm going to use Mosaic data for is the ultimate blueprint for assessing how well satellites are doing in measuring sea ice properties. and finding pathways to improve those measurements. And the thing that I'm most excited about is seeing what new information we can get of the sea ice cover from satellites. So for example, NASA launched ISAT-2 last year. This is a laser altimetry mission to measure surface elevations and sea ice freeboard, which we can get sea ice sickness from. I want to see if we can get new information about melt ponds in terms of their coverage and their depth, which has important implications for the ice albedo feedback. Okay, so June is still pretty far away. It's about 6 months away, and as Steffi alluded to, there's a lot of changes going on. And one thing that I'm a little concerned about is how much is the ice cover going to change between now and then? And what I want to illustrate to you is an example from this expedition called Sheba that happened in the late 1990s. And what you're seeing is this square box. It's outlining sea ice. This is from satellites. And this is about a 50 kilometer by 50 kilometer area. And what you're going to see is the ice motion over a 6-month period. So pretty much the same seasons, but between 1997 and 1998. And as you can see, the ice is incredibly dynamic. It's moving with the winds and the ocean currents. And I should note that this is old ice. It's much thicker. It's much more resilient than what we're seeing at Mosaic. Mosaic has exceptionally thin ice. It's seasonal. It's less extensive. And for these reasons, it's a lot easier to get pushed around by the winds and ocean currents. So it's much more dynamic. So yeah, at the end of 6 months, you can't recognize the square anymore. So to recap, what Mosaic is seeing is a sea ice cover that's incredibly thin and less extensive, in fact, ever than before, based on our satellite records and submarine records. And because it's thinner and more seasonal, it's more sensitive and more dynamic to these events, to these weather events, to atmospheric forcings and ocean forcings. And for this reason, we need to go out there and better understand how the atmosphere, the ocean, and the sea ice interact with one another, not just for a snapshot in a given year, but for a full annual cycle. This will really revamp our baseline understanding of how the Arctic system works. And while gaining new knowledge is really important, this is actually quite critical for improving our predictive capability in forecasting what will happen, or not just forecasting, but projecting what the future state of climate will be like, what its effects are on our weather, and also on our ecosystems and society itself. So we've had a lot of discussions on the ice being thinner or unusually thin from Marcus and from Matthew. So if you're interested in what the conditions were like leading up to Mosaic, I'd encourage you to stick around or at least come back at 11 o'clock for NOAA's Arctic report card release. This will have everything that you wanted to know about all the past conditions of sea ice this past year. I don't know what that is. And what we're experiencing on Mosaic now. Okay, thank you very much.
All right, thank you. It sounds like we still have the Polar Stand on the line. Marcus and Matthew, are you still there? Okay. Well, Katie, can you go call them back, and we'll start opening questions for the panelists that we have here in California. Are there any questions from reporters in the room? Nobody? Sarah?
Sally, you talked about the difficulty of getting data back from the Polar Stern, but I'm wondering, is there either based on sort of the observations that have been made so far and some of the data that has come back, is there anything that we can say that we've learned in the past 3 months that we didn't know before, or things that we're starting to, things that are starting to be revealed by having the ship up in the Arctic where it is?
Is this on? Yes. Okay. I think that most of the scientists have been so busy preparing for Mosaic and working with the instruments on board. I haven't heard a lot yet about whether there's anything that they've seen from the atmospheric data that's new or unexpected. I know the sea ice conditions have been quite challenging, but I haven't heard yet about whether the atmospheric data is what they expect or not.
Well, yeah, so as was already mentioned, so it's of course pretty tough to get all the data back, and the people are really busy with just maintaining the camp and setting up all the stuff again after all those major storms. However, I mean, also this is already one result in the end, of course, that really the entire system is pretty dynamic. And this is something really, I think this will be kind of the key element in the end for Mosaic to get used to that really dynamic system, which is new for us. And yeah, to work in that environment.
More questions from the room? Okay, we have the ship back on the line if people would like to ask questions from our scientists on Polar Stern.
Hello, Polar Stern. It's Jonathan Amos from BBC News here. I mean, it kind of sounds that the message you have for us really is the difficulty you've had in setting up the camp. That's kind of the message, isn't it? Conditions now are not what they were 10 years ago, and you prove that.
That is correct. That was one of the biggest challenges we faced here when we came, that the ice was so thin that it was hard to find an ice floe which provides the stability that we need for setting up a research camp for a full year and for mooring a vessel, a massive research vessel, to that floe. But after some time, we have been able to find a nice floe which in large part reflects the standard ice conditions of the modern Arctic, which is not part in and has been eroded during summer as all the other floes, but which has a more stable core, which serves as a basis for our logistical setup. And from there, we now spread out to the thinner parts of the ice so that we can do our research on the ice that is characteristic for the region, while at the same time have a more stable hub for our operation.
More question.
Hello, Polar Stern. This is Christoph Seidler from Der Spiegel. Marcus, I have a question. You told us about the dynamic starting phase. How about the next month, the winter time? Is that a time with the lower temperatures, but still where you can expect a little bit more stability and are not busy only rearranging the camps on the ice floe, but actually get even more work done?
Actually, the dynamics of the ice continues. I think it was about 10 days ago, a major fracture zone formed right through the middle of our research camp. One half of the research camp drifted sideways by 500 meters. All the power lines were ripped and destroyed during that event. All our tracks and roads have been destroyed. But within days, we just reconnected everything, and we constructed new tracks and roads, and the things were up and running just a few days later. And we have done that a number of times now. We just constantly adapt to the changing ice environment here, and we will continue to do so. It is hard to predict what is going to happen now during the rest of the winter. The ice is going to get thicker, but I think some significant ice dynamics we have to expect for the whole year.
We have more questions from the room. Do we have any questions on the chat? Oh, sorry, we have Sarah Kaplan.
Marcus and Matthew, can you talk a little bit about that storm that happened in November? Sort of what were the conditions like? What did the team do during the storm where you're sort of hunkered down on the ship? How long did it last? Just sort of paint a picture for readers about what that experience was like.
Well, the storm was actually pretty fantastic, and it's something that, we knew would happen, and it was a tremendous opportunity for us to understand something that's really important here in the Arctic system. That storm made a lot of ice dynamics happen, and that made it challenging for some of our observations on the ground, as Marcus described earlier. And so there were some interruptions in some of our measurements, but fortunately we have a lot of measurements that are ongoing, a lot of measurements on the ship. We have routine radio sondes, remote sensors looking up the atmosphere. So we did a tremendous job of capturing the storm, capturing the kind of effect that it had on the atmospheric structure, on the precipitation, looking at how it affected the energy budget of the sea ice, and going all the way down through the ice and into the ocean and causing ocean mixing. And so it's really, I think, a great example of what Mosaic's all about, looking at the effect of these kind of big events in the coupled system on all parts of the system and how they interact with each other.
Actually, I think for the first time we have been able to study the impact of such a system, of such a storm with this comedy and on the fully coupled Arctic climate system between atmosphere, ocean, and sea ice. So it has been a unique opportunity, and we have used it well. I think we have a fantastic data set.
I think it's probably pretty unique that you guys would say it was an amazing opportunity and not like it was kind of scary or, you know, a lot of people, the idea of being out on the sea ice in the middle of a storm like that would be intimidating. Was there any aspect of it that was, I mean, just can you sort of help people understand the size of it or the speed of the winds, how long it lasted?
Actually, it was a pretty significant storm event. It lasted for a couple of days, and of course it was scary. Many cracks in the ice formed. We had to go out in the middle of the storm to rescue some of our equipment, some of the equipment actually out of the water. And that is sometimes not nice to work out there in the storm at very low temperatures. But at all times, it was on our mind, wow, this is a fantastic opportunity. We are the first team. We have been the first team who has the chance to observe the impact on such a storm system throughout the system with such a comprehensive set of measurements. And I think so. It's both. We were all excited about it, and of course, it was scary.
Yeah, I would emphasize that as well. Just really, there was a lot of smiles on people's faces, a lot of excitement, especially with the dynamics in the ice. Right, it really created these amazing open areas, these leads that came through, and then ridges. And it's just a pretty exciting place to work because every day your commute out to your station out on the ice is different. And I think that was exciting for people. It was kind of that kind of new frontier exploration kind of feel that people, I think, really kind of resonated with, and it kind of made them excited.
Harvey Lyford, freelance writer. I'm interested in the polar bears. We were looking at an image of two polar bears at one of your flags, and it looked as if they had actually erected the flag. But I don't suppose there's a lot of data on the normal number of polar bears that far north, and I was surprised that there are any because they would have an awfully long walk or swim as the ice begins to break up. So do you have any kind of data about that, or are people surprised to see the bears that far up?
Actually, it is not very well known how many polar bears live in the Central Arctic in the middle of the polar night here on the ice. There are individual bears which are tracked with GPS systems, and people know that they wander through the Central Arctic even in winter, but there aren't any statistics. Our own statistics show there are many. We have so many polar bear visits. We have to stay extremely alert that we avoid confrontations and approaches of bears to humans. So once we see a bear somewhere, we immediately go back to the vessel so that we don't get into close contact with the bear, which could be dangerous for both sides, and we do everything to avoid that. We have a staggered system to detect polar bear approaches, starting with thermal infrared camera systems and night vision equipment to be able to detect if a polar bear is in the area.
Do we have more questions from reporters in the room? Questions from the chat? No? All right. Well, we'd like to thank our panelists and our scientists on the Polar Stern for joining us today. And we'll resume at 9 o'clock for the next press conference.
right, welcome to our 9 o'clock press workshop on climate change and El Nino. Does global warming matter for the climate of the tropics? With us today, we have Christina Karam-Peredu from the All right, welcome to our 9 o'clock press workshop on climate change and El Nino. Does global warming matter for the climate of the tropics? With us today, we have Christina Karam-Peredu from the University of Hawaii at Manoa. We have Jessica Tierney from the University of Arizona, Pedro Denizio from the University of Texas at Austin, and Mark Kane from the Earth Institute at Columbia University. I'm going to turn it over to Christina.
Thank you for the introduction, and thank you all for being here. So this year's theme at AGU is to celebrate the past and inspire the future. So I think it is fitting to start with the note that a lot of the early understanding and research on El Nino Southern Oscillation and its impact both in the tropics and outside the tropics is
University of Arizona, Pedro Denizio from the University of Texas at Austin, and Mark Kane from the Earth Institute at Columbia University. I'm going to turn it over to Christina.
Thank you for the introduction, and thank you all for being here. So this year's theme at AGU is to celebrate the past and inspire the future. So I think it is fitting to start with the note that a lot of the early understanding and research on El Nino Southern Oscillation and its impact both in the tropics and outside the tropics is based on this seminal paper by Jacob Bjerknes. It was written 50 years ago and is entitled Atmospheric Teleconnections from the Equatorial Pacific. And as the seminal paper by Jacob Bjerknes, it was written 50 years ago and is entitled Atmospheric Teleconnections from the Equatorial Pacific. And as the title reveals, Bjerknes really made the case for when we have temperature anomalies, warm temperatures in the tropical Pacific, that affects weather and climate outside of the tropics. And also he made the case that this is a coupled atmosphere-ocean phenomenon, meaning that you need the ocean and the atmosphere processes to interact in certain ways to give you the development of an El Nino event. So Bjerknes didn't have much to work with back then. He based his conclusions on three El Nino events, the 57-58, the 63-64, and the 65-66. So as you see here from this record of 17 years, title reveals, Bjerknes really made the case for when we have temperature anomalies, warm temperatures in the tropical Pacific, that affects weather and climate outside of the tropics. And also he made the case that this is a coupled atmosphere-ocean phenomenon, meaning that you need the ocean and the atmosphere processes to interact in certain ways to give you the development of an El Nino event. So Bjerknes didn't have much to work with back then. He based his conclusions on three El Nino events, the 57-58, the 63-64, and the 65-66. So as you see here from this record of El Nino index, where red indicates an El Nino event and blue indicates a La Nina event, these three events are relatively small or moderate. And since Bjerknes died in 1975, I believe, he didn't have the chance to experience and study the three largest El Nino events we've seen. The 1982-83 event, which was devastating for, especially for the Far Eastern Pacific, the Galapagos, and the marine life there. The 97-98 event, which is very famous for the extreme rainfall in California and also the devastating impacts in El Nino index, where red indicates an El Nino event and blue indicates a La Nina event. These three events are relatively small or moderate. And since Bjerknes died in 1975, I believe, he didn't have the chance to experience and study the three largest El Nino events we've seen. The 1982-83 event, which was devastating for, especially for the Far Eastern Pacific, the Galapagos, and the marine life there. The 97-98 event, which is very famous for the extreme rainfall in California and also the devastating impacts in Peru, and also famous by Chris Farley and Yoshua El Nino. And the larger, most recent one, the 2015 Peru, and also famous by Chris Farley and Yoshua El Nino. And the larger, most recent one, the 2015-2016 event. So in a sense, 50 years and three large El Nino events and 3 generations of researchers later, we have much more, many more lines of evidence to go on to understand El Nino. So not only do we have satellite observations, but we also have a dedicated observing system in the tropical Pacific of buoys that are maintained by NOAA. We also have paleoclimate records, and my fellow speakers will in 2016 event. So in a sense, 50 years and 3 large El Nino events and 3 generations of researchers later, we have much more, many more lines of evidence to go on to understand El Nino. So not only do we have satellite observations, but we also have a dedicated observing system in the tropical Pacific of buoys that are maintained by NOAA. We also have paleoclimate records, and my fellow speakers will elaborate on that. And we have model simulations from numerical models that are limited to simulating the tropical Pacific, like the famous Zebia-Kane model, Kane being the gentleman present here, which was used to make that. And we have model simulations from numerical models that are limited to simulating the tropical Pacific, like the famous Zebia-Kane model, Kane being the gentleman present here, which was used to make the first successful prediction of El Nino using a model back in 1985, to the state-of-the-art sort of Earth system models with all the bells and whistles that we have today. And all of these new lines of evidence in these past 50 years corroborated the view that Bjerknes had, that, and added more complexity to that El Nino is such a complex phenomenon, and you need all these processes, including upper ocean physics, and also, very importantly, the physics of clouds, both the high clouds and in the West Pacific over the warm waters, and first successful prediction of El Nino using a model back in 1985, to the state-of-the-art sort of Earth system models with all the bells and whistles that we have today. And all of these new lines of evidence in these past 50 years corroborated the view that Bjerknes had, that, and added more complexity to that El Nino is such a complex phenomenon, and you need all these processes, including upper ocean physics, and also, very importantly, the physics of clouds, both the high clouds and in the West Pacific over the warm waters, and the low clouds in the East Pacific over the cold waters. All of these to really come together, Pacific over the cold waters. All of these to really come together in a perfect storm to give you a big El Nino event or a La Nina event. And it is important to note here that we have El Nino events in our models, and there's no, that arise spontaneously from the model solving the equations of motion of the ocean and the atmosphere. So by representing the processes that are important for an El Nino development, the models create El Nino events, but there's no switch that you turn on to say, well, model, you need to have an El Nino, right? So together in a perfect storm to give you a big El Nino event or a La Nina event. And it is important to note here that we have El Nino events in our models, and there's no, that arise spontaneously from the model solving the equations of motion of the ocean and the atmosphere. So by representing the processes that are important for an El Nino development, the models create El Nino events, but there's no switch that you turn on to say, well, model, you need to have an El Nino, right? So The other aspect of El Nino that the Bjerknes didn't or couldn't know back then that we are very interested in the past few years is that El Nino comes in many flavors. The other aspect of El Nino that the Bjerknes didn't or couldn't know back then that we are very interested in the past few years is that El Nino comes in many flavors or many faces. We have events where the sea surface temperature warming is more, is concentrated in the East Pacific or more in the Central Pacific. And what is important about these flavors of El Nino is that their impacts are different. So this plot here shows flavors or many faces. We have events where the sea surface temperature warming is more, is concentrated in the East Pacific or more in the Central Pacific. And what is important about these flavors of El Nino is that their impacts are different. So this plot here shows the impact on precipitation. Blue colors mean you have more, and the brown colors mean you have less precipitation when you have each one of these El Nino events. So I think we can all appreciate that we have areas where if you have one type of El Nino, you'll get the impact on precipitation. Blue colors mean you have more, and the brown colors mean you have less precipitation when you have each one of these El Nino events. So I think we can all appreciate that we have areas where if you have one type of El Nino, you'll get more rainfall, but if you have the other type of El Nino, you'll actually get less rainfall. So obviously the holy grail or the important questions out there is whether all of these will change in a warmer world. And however El Nino itself might change in a warmer world, it will be superposed on a altered state of the mid-tropical Pacific. So you see here, this is from the most recent IPCC report. The majority of models project that with a warmer world, you will have more of this warming in the East Pacific on average and get more rainfall. But if you have the other type of El Nino, you will actually get less rainfall. So obviously the holy grail or the important questions out there is whether all of these will change in a warmer world. And however El Nino itself might change in a warmer world, it will be superposed on a altered state of the mid-tropical Pacific. So you see here, this is from the most recent IPCC report. The majority of models project that with a warmer world, you will have more of this warming in the East Pacific on average. And this pattern looks a little bit like what we see during an El Nino event. So the question, this pattern looks a little bit like what we see during an El Nino event. So the question there is whether the way that the mean climate changes in the Pacific is related to how El Nino itself is changing, whether you see more El Nino events or less El Nino events, stronger or weaker. And this is a very complex question to answer, but I believe we are making progress. If you look at this, the pattern of whether you are more El Nino-like or La Nina-like as you respond to greenhouse gas warming. This is for a high emission scenario from the most recent generation of models, versus the percentage of change that you can see in El Nino activity, then you see there's a relationship there that becomes more consistent when you're looking at the models that do a little bit better in representing basic El Nino character. There is whether the way that the mean climate changes in the Pacific is related to how El Nino itself is changing, whether you see more El Nino events or less El Nino events, stronger or weaker. And this is a very complex question to answer, but I believe we are making progress. If you look at this, the pattern of whether you are more El Nino-like or La Nina-like as you respond to greenhouse gas warming. This is for a high emission scenario from the most recent generation of models, versus the percentage of change that you can see in El Nino activity, then you see there's a relationship there that becomes more consistent when you're looking at the models that do characteristics, including that those El Nino flavors that I was just talking about. And the other important aspect of how models are simulating El Nino is that their skill in doing that is a good indicator of how they're generally performing in simulating processes like clouds, for example, and cloud radiation feedbacks that are important not just for climate change in the tropical Pacific, but also globally. The good news is that model simulation of the mean tropical Pacific climate and El Nino is improving. This is a plot that shows do a little bit better in representing basic El Nino characteristics, including that those El Nino flavors that I was just talking about. And the other important aspect of how models are simulating El Nino is that their skill in doing that is a good indicator of how they're generally performing in simulating processes like clouds, for example, and cloud radiation feedbacks that are important not just for climate change in the tropical Pacific, but also globally. The good news is that model simulation of the mean tropical Pacific climate and El Nino is improving. This is a plot that shows the equatorial temperature. So the middle lines here indicate the tropical, Pacific. So you see that going from the previous generation in blue to the next generation of models in red, we come closer and closer to observations in black. Models are indeed improving. They're improving also in how they simulate El Nino processes. But key challenges remain, of course, and there's a lot of room for even more improvements so that we can have more confidence in the future predictions of El Nino. So I think that, and this is very important because obviously that gives us more skill Pacific. So you see that going from the previous generation in blue to the next generation of models in red, we come closer and closer to observations in black. Models are indeed improving. They're improving also in how they simulate El Nino processes. But key challenges remain, of course, and there's a lot of room for even more improvements so that we can have more confidence in the future predictions of El Nino. So I think that, and this is very important because obviously that gives us more skill to understand the global impacts of El Nino, a schematic of which you see here. So I think hopefully if I, or Bjerknes for that matter, have convinced you that the tropics rule. We have organized a session this afternoon based exactly on these 50 years since we have had this seminal Bjerknes paper. And the session is entitled after the Bjerknes session, so atmospheric teleconnections from the equatorial Pacific at 4 p.m. today. Thank you.
My name is Jessica Tierney. I'm actually a paleoclimatologist, so I study climate changes in the past. And the reason I do that is I'm interested in using the past to give us a better idea of where we're headed in the future, including the tropical Pacific. So the main point that I'll present to you today is our recent finding that the Pliocene past, so that refers to a time 3 million years ago, predicts the future of the tropical Pacific. So we actually have a really nice direct analog of where we're headed in the near future by looking back 3 million years ago. So let me explain what I mean by that. So first of all, let's just consider the structure of the Central Pacific. So the trade winds are blowing from east to west here, and because of that, the warm water tends to pile up next to Indonesia here, and it has a really technical name. It's called the Whirlpool. And on the other side of the Pacific here, because the winds are blowing this way, you have cold water coming up, so we have our second technical name, which is the cold tongue. And these are both warm places in the tropics, but you can see from the temperatures there that there's about a 5 degrees C difference between the east and the west Pacific, so it's pretty substantial, 8 degrees in Fahrenheit scale. But if we look at the geological evolution of the eastern and western Pacific, we can see that this difference has not always been the same. So here I'm showing you a result from a recent paper that we published in AGU's Geophysical Research Letters this year. It's the evolution of sea surface temperatures in the Western Pacific in the red line and the Eastern Pacific in the blue line. The x-axis is the age in millions of years. And so if we look here on the right, this is time 0, that is today. We see that classical difference between the east and west is 5 or 6 degrees. But as we go back in time, these lines come together. And so when we go back to the Pliocene epoch, which is denoted up here at top 3 million years ago, we see that there's still a difference between the east and the west. There has to be because the trade winds are blowing, but it's much lower. And this is significant because the Pliocene is the last time that CO2 was where we are today, 400 ppm. So that was the last time that we are where we are today. So this is basically giving us a signal of what to expect in the future. In this paper, we also went one step further, and we actually put together maps of what sea surface temperatures looked like during the Pliocene, that 3 million year time period. So that map is here on the left for you. It's the increase in sea surface temperature relative to a pre-industrial baseline. So we're looking at an anomaly plot here. And similar to some of the figures that Christina showed you, we see this classic pattern in the Pliocene of warming in the Eastern Pacific here, and also the subtropical warming pattern, very high sea surface temperatures off of California, which is a typical response and associated with this change in the mean state of the tropical Pacific. On the right-hand panel, that's actually a prediction of what the Pacific will look like under a low emission scenario, the RCP 2.6 from the last IPCC AR cycle. And so low emission scenario basically has us holding at 400 ppm, going up to 500 and staying there because we have strong mitigation strategies. Nonetheless, we see that the pattern of change in the tropical Pacific, it really looks a lot like the Pliocene, right? So this is the key message, is that the Pliocene is the key to our future. It's sort of confirming that this pattern that's produced by models is realistic because we actually see it in the geological record. And so this is important for a couple of reasons. The first is there's actually been an ongoing debate in the scientific community about whether the average conditions in the tropical Pacific will resemble an El Nino, what we call an El Nino-like state, or conversely, a La Nina-like state. And there's reasons to expect both, and different models do slightly different things. But the Pliocene, it enables us to rule out the hypothesis that this is actually a feasible response to high CO2, because the Pliocene is telling us that this is what we should expect. And this is, of course, as Christina mentioned, really important for rainfall patterns around the world. So here we're looking at projections in mean annual precipitation under the low emission scenario, RCP 2.6, sort of maintaining at present day CO2, versus the high emission scenario, RCP 8.5, where we continue to burn fossil fuels. And so you can see, I sort of circled the regions where we expect responses in rainfall associated with the change in the tropical Pacific, that El Nino-like pattern. So we see more rainfall all along the equator in the Eastern Pacific going into Peru. Also, an area that's affected by the tropical Pacific, even though it's farther away, is the Middle East, right here. And I've also drawn a circle around where we are right now in California and sort of southwest United States more generally, because this is a place where we expect the mean state of the tropical Pacific to impact rainfall. We actually expect it to increase the rainfall here. But you can see from these projections that it's not clear how California will fare under higher CO2. It's right on the edge between the sort of blue-green and the brown color. Again, we can go back into the past and get some clues. So where I live in western Arizona, we actually see all over the place evidence of large lakes during the Pliocene, that 3 million year time period that I'm talking about. So this is an example of an ancient lake basin in western Arizona. If you've been to Arizona, you know it's a very dry place. We don't have permanent lake basins down there today. There are quite a few of them during the Pliocene. So that is a clue that we're now investigating to follow up on. Why was the southwest US actually wetter during the Pliocene? So some related talks that are happening tomorrow and Thursday would be my own talk. It's sort of about the last glacial maximum, what we can learn about that, but in particular, Dr. Tripti Bhattacharya will be giving a talk about that question about the Pliocene and why it might be wetter in the southwest US.
Hello, everyone. My name is Pedro D'Inesio. I'm a climate dynamicist, but I like to work with paleoclimatologists like Jessica, trying to understand the past to understand the future. My take-home message is that there was an active El Niño in the Indian Ocean. The Indian Ocean, we haven't talked yet about it, is an Indian Ocean that today is not climatically active. It's quite stable, but 21,000 years ago, it was extremely active. And 21,000 years ago, it was not a warmer climate, it was a colder climate, but still serves us to understand how the tropical oceans respond and can hold these surprises that all of a sudden a whole basin, an ocean that is now inactive can become active. So how that happens? So the modern Indian Ocean is the least climatically active of all the tropical oceans. So here I'm not showing the mean state of the Pacific like Jessica showed, but how variable it is. So the colors in this map show the magnitude of year-to-year fluctuations in sea surface temperatures. We control the rainfall in all tropical oceans. And you can see El Niño with the largest variability. And then when you focus on the Indian Ocean, there's not a lot going on. If you look at the shading, there's a bit of variability off the coast of Sumatra and Java here, which we call that the Indian Ocean dipole, but there's no large-scale fluctuations in sea surface temperatures, which would then bring large-scale impacts in rainfall. So we know that this variability is controlled by the mean state. And we also knew that 21,000 years ago, the Indian Ocean could have favored a more active Indian Ocean. So we tested this hypothesis with Kaustubh Tirumalai, who cannot be here today, while he was doing a postdoc at the University of Texas. And this hypothesis was based on a prediction from a model. So here in the shading, you can see the change in the variability that this model predicted. This is a fully coupled global ocean atmosphere climate model with all the bells and whistles, and then we changed the boundary conditions to simulate the last ice age 21,000 years ago. And the model predicted this increase in variability that you can see here. These are changes in a percentage relative to a baseline. So you can see changes up to 100%. That's a doubling of the magnitude of the variability off the coast of Sumatra. So we have sediment cores that store climate information in sediments in the bottom of the ocean. There's ships that you can send to get those cores, those sediments, and then analyze them and extract climate proxies from those bags called G-rubber, and then from them estimate how the variability was, because each one of these bugs, these foraminifera, they're microscopic. You have to look at them on the microscope. That's Kaustubh looking at the microscope. And in the sediments, and each one lives for a month. So it gives you a snapshot of 1 month. So if you look at many of them, you can have an estimate of how variable things were at any given time in the past. So Kaustubh looked at the microscope and picked almost 1,000 of these bugs to compare a pre-industrial baseline with this last glacial maximum 21,000 years ago, and then estimated the changes in climate variability back then in those 4 sites, and then we compare them with the model. So here in circles, you have the measurements, again, the relative change, so you can see these are huge changes, and in the boxes, it's the model. And you can see that these are equations solved on a computer, and which we are comparing with geochemical measurements made on these microscopic bugs, and they all match quite nicely, showing this massive increase in variability in the Indian Ocean, which tells us that the Indian Ocean, although it's inactive today, it can become active and produce this variability that can produce unprecedented climate extremes. And in our simulations, the variability looks like in this plot. So here we're not looking at changes in mean state, it's just how the fluctuations look relative to that mean state back 21,000 years ago in the Indian Ocean, and that's an El Nino in the Pacific. That's the latest El Nino in 2015, 2016, and you see that the patterns are quite similar. The magnitude is not as large, but it still can produce unprecedented hydrological extremes in all the countries surrounding the Indian Ocean. So the Indian Ocean could become active in the future, causing unprecedented climate extremes. I won't show you any figures because that paper is not published yet, but I'll be talking about those results today. Later, at the end of the day, at the Viernes session. And then there's other related talks about how these changes in El Nino can produce new extremes, and all the glorious details about changes in El Nino on Friday.
I don't have any slides, which is always a challenge for people like me because we're used to using them as a crutch. The three younger people who've spoken ahead of me have given you a good overview of a great deal of what we've learned in the 50 years since Bjerknes wrote this landmark paper. In fact, most of what they talked about is probably comes out of the last decade or perhaps a little more, which is really amazing. The level of progress is in many ways quite astonishing. One of the things I'll emphasize first is the work on the Pliocene that Jessica talked about. There isn't a lot of support for research on the Pliocene compared to what I think there should be, given that this is indeed the last time the planet temperatures, CO2 levels, looked like what they're about to look like. And you would think there would be a more urgency in learning more about what the Earth was exactly like then. And as Jessica said, the message seems to be in line with most, but not all models, but most, that things will get to a more El Nino-like state, and one of the implications of that would be the expectation that California and Southwest, like Arizona, would get wetter. I'll come back to that in a second. Now, as Christina emphasized, well, she didn't emphasize this, but the first thing I want to say is we're not really sure what will happen to El Nino in the years ahead. But the more solid expectation is that you add El Nino to the warming that is certain, okay, and these kind of extreme events get worse. That's true of many other sorts of extreme events, like tropical cyclones, hurricanes. Okay. And so whatever happens to El Nino, we know that the consequences of it will be worse. One of the things we're sure of about the future is that when it rains, it's going to tend to rain harder, okay? And El Nino will make it rain in some place. And when it's dry, it's going to be drier. And in other places, El Nino will have that tendency. That, in a way, is good news. We've made predictions now of El Nino. We have learned something, particularly at an institution I helped to found, the International Research Institute for Climate and Society, has learned a great deal about how to use these predictions to help people in places in Africa and Asia and so on, the kind of developing world countries where it's not a given that, say, some bright young commodities broker or hedge fund manager or something will jump on whatever information you have to offer. Now, on the bad side, Well, let me start it this way. My PhD advisor was a man named Jule Charney, who was responsible for the first weather forecasts. And toward the end of his life, in 1980, he expressed to me a great disappointment about how little progress there'd been in weather forecasting since the 1950s. Okay. And since then, I'd say that weather forecasting has made enormous leaps, and a good bit of that has been, I would attribute to two things. The first and probably most important is the just incredible growth in computer power since that time. We made an El Nino model in 1985, and we would run it to make forecasts, and we would run out a year or two. And what took us an hour to do then takes on as big a computer as we could manage, okay? Now it takes about a second on one of those things that you all have in front of you. Okay. That makes a huge difference in what you can accomplish. On the other hand, I have to say, as somebody who pioneered this kind of forecasting, I'm kind of disappointed too in the lack of progress that we've made in seasonal to interannual forecasting. And part of this is the same issue that compared to the size of the problem, the computing resources are still a little substandard. The other thing I think is that we haven't organized ourselves terribly well to do either the, let's say, decadal forecasting, interannual forecasting, decadal forecasting, or really, to be honest, the problem of forecasting anthropogenic influence on climate change for many years ahead. Okay. It would take, let's say, a more concentrated effort with an enormous amount of more computing power. We know that this would help because we've done enough experiments to see that. The other thing that goes with this is, in particular for the El Nino problem, okay, most of the models tend to do have strong biases in what the normal, the climatological seasonal cycle is in the Pacific. When you have those biases, you tend to get the variability wrong in some ways. And certainly it's harder to be confident in what you're predicting. Okay. So that's something that needs more work. The hopeful note is that there are many people now working these problems. It would go a lot faster if the efforts were better funded and better organized. Thank you.
Thank you, Mark. We'd like to invite questions from our reporters in the audience. Does anyone like to ask a question? Christoph?
Christoph Seidler, Der Spiegel in Germany. Just a very general level question, but you've all briefly touched upon this, but still maybe we can have an extract in layman's terms. So what will the future bring for El Nino? So of course we've heard a bit, but can you condense it a little bit for me?
I can start. I think what most of us have mentioned is that there is a range of possible outcomes coming from the models. There is model disagreement that depends to a big extent on how models are representing mean climate or the seasonal climate that Mark just mentioned. So it is still uncertain. There's I have in my talk a review paper that is a good reference for the most recent information on this. There's papers recently that show that if you segregate the models based on how well they represent some of the aspects of El Nino, then those models tend to agree more that there will be more frequent, strong El Nino events. But this is still very much of an open question, and there is a lot of uncertainty there.
I don't know. Yeah, I just want to. So there's two aspects here. One is the average state of the tropical Pacific, and the other is El Nino, actually up and down, like from year to year. And so, and both of those things are still in question. But so what I emphasized was that the average state looks like it could become more El Nino-like, just based on what we see in the past during times of high CO2. And quite a few climate models predict that. They did in the last IPCC assessment, and then new results that are just coming out suggest a similar thing. So, so it's not for sure, but so we sort of understand that the average condition looks more like an El Nino event, if you will. In terms of El Nino itself, year to year, that's a little bit more scattered. And so what Christina shows, there's a tendency for models to predict stronger El Nino. But on the other hand, if I've got this right, that some of the best models, the ones that simulate El Nino correctly, actually have a more stable response. So, El Nino, I think it's still out there whether individual El Nino events will get more extreme. And we expect in a warmer climate that we have more extreme rainfall and so on. But as far as El Nino goes, that's like still a top question in our research community.
Yeah, but as Mark emphasized, the impact are certain to become stronger because you're in a warmer atmosphere. So every time there's an El Nino causing a deluge, it will just rain more. And we know that will happen because it's controlled by atmospheric thermodynamics. So, I mean, I like to see this problem as a risk assessment. If there's, we will never know if El Nino got stronger. No one will be here, and it's a very hard statistical problem. But what if in 5 years from now there's another big El Nino? We had the strongest El Ninos on record in the last 30 years. So that's suggesting something, but it's hard to tell what caused them. But what if we have another one? So how do you attribute whether that event was made worse by a changing climate or not? But so I think we cannot rule out that it won't change, but there's this risk that if a big El Nino happened in the next decade, it will have been influenced by changes in climate, and the impacts will still be stronger. And also, the one thing to keep in mind that the global impacts, and those are the teleconnections that Viernes talked in the title of the paper, that's how the impacts are propagated from the equatorial Pacific to everywhere in the world. Those teleconnections can be shifted as the eastern side of the Pacific warms up, then the teleconnections also move to the east. So here in California, you get all that rain when there's an El Nino. On average, not every El Nino brings more rain, but on average. But that average pattern can also shift to the east. So sometimes the rain can move also even though El Nino doesn't become stronger. So I think it's pointing to changes. And when you shift the pattern, you can go from being impacted one way, and you're used to that, and then you're impacted in a different way, and you're not used to that. But I think probably Mark will say that too, is that we can predict El Nino. So even if the impacts get stronger, we can like 6 months, maybe 8 months in advance, we know when El Nino is coming, and probably every El Nino will be having worse impacts every time. But we have those months that can help societies prepare.
So the quick summary is the impacts of El Nino will get worse. Okay. Exactly what happens to El Nino is hard to say, and not clear it matters a lot in the sense that even before we started really messing up the atmosphere, the variability in how El Nino occurred was quite extreme, and that might continue. It's true we've had a lot of strong El Ninos, maybe the strongest in recent years. On the other hand, at the end of the 19th century, there were also very many strong El Ninos, and the most destructive El Nino in the last few hundred years was in 1877. Okay, probably tens of millions of people died in famines in India, China, Ethiopia, northeast Brazil, and other places. So this has always happened, but it will, on average, be getting worse. Another thing I could say about it, just to go back to what we don't know, is I've been involved in some work that says, well, as you know, anybody who lives in California certainly knows, it's tended to be dry in recent years, and the tropical Pacific has not yet gone into the state we expect of looking more El Nino-like. It looks more the other way, which is what goes with dry in California. Okay, and we've done some work which suggests to us that this is highly unlikely to be due to some random internal variability. That is, it seems far more likely to be some sort of at least transient response to the way we've mucked up the atmosphere already. Okay, but our models aren't getting this. So that's kind of a problem for us. In other words, yes, you can worry about El Nino in the future, but we could also start by asking, why aren't we doing a better job on now? Because I'm sure people in California would like to know whether in the next 2, 3, 5, 10 years, it's likely to rain more or not.
Hi, I'm Mary Miller from the Exploratorium. One of the impacts of El Nino is a reduction in upwelling in Peru. Of course, there's also upwelling in California that's very important for ocean ecosystems. I'm wondering if any of the models have enough resolution for you to say what might be happening to upwelling in the future.
No, there's ways to know, because upwelling is still, even though it happens on the coasts and you think it's small scale, but it's controlled by winds, and in the Pacific everything is coupled. It was also in Bjarne's paper. I mean, everything was in Bjarne's paper. If you read one sentence, it was just like the seed of everything we've studied over the decades. But so these patterns, like the one that Jessica mentioned, when as the planet warms up, the eastern side of the Pacific warms up faster or more, that weakens the trade winds. So it will weaken your upwelling. And that's controlled by, we know that very well. It's not uncertain, it's just mechanics, it's Newton's laws. And so on the equator, if that pattern emerges, upwelling is expected to weaken following the trade winds that are controlled by that contrasting warming between one side and the opposite side of the basin, because air on the equator likes to flow from colder to warm. Then if you focus on away from the equator, because Peru is away from the equator, there's other factors that are mattering, and there's other wind patterns that will control the upwelling there. Same thing in California. But there's huge fisheries also on the equator that will be influenced by those changes.
Yeah, I'll just add that one thing that is worrying to me is that in our assessment of the Pliocene 3 million years ago, the temperatures that we're seeing in the California current and the Peru margin are really toasty, like 7 degrees Celsius warmer. And we have quite a few data points off of California in particular, so that result keeps coming up. And actually we see it elsewhere, like off of South Africa and the Benguela upwelling. So this worries me because the magnitude that we're seeing in the past is, to me, extremely large. So assuming there isn't something wrong with our data, then we need to explain that, whether that's realistic or not, and whether that has to do with the upwelling zones having this really strong response to high CO2. Maybe it involves cloud feedbacks potentially. So that's something that we're definitely looking into.
As scientists, we're always very cautious, so we don't like to say anything unless we're pretty certain. But if you were doing it from, let's say, a risk assessment point of view, then you would have to say that it's highly likely that the upwelling, you'll go into a more El Nino-like pattern. The upwelling will be diminished. The ecosystems will be disrupted. Some of them perhaps will succeed in moving poleward. Other ones will not. That's the more likely outcome, although from, using the scientific standard of certainty, we wouldn't say we're terribly confident of that. If you're worried from a risk point of view, you would say, yeah, this is a huge risk. You shouldn't be exposing yourself to it or the planet to it.
Aaron, do we have any questions on the chat? One question.
David Appel, freelance, wants to know, is there an underlying reason for why El Niños and La Niñas occur?
Yes. Go ahead, you explain it.
Oh, okay. You have about 2 minutes.
I have about 2 minutes to. I think it goes back to the introduction with those that schematic that has all these processes that come together. I think the question is about that, right? How do you get to have El Niño event? So every few years you have the trade winds slackening. So you have what we call westerly wind bursts. So anomalous winds that translate into a weakening of the trade winds, and then that gives you a heat signature, in a sense, in the East Pacific. You have that warming that comes through a subsurface heat wave, you can say. So then that warming leads to a shift of the strong precipitation sort of centers from the West Pacific more to the Central Pacific. And from that emanate all these teleconnections outside of the tropics. So it is what I mentioned in the presentation. You need, in a sense, a perfect storm of a lot of processes, the westerly wind sort of bursts in the west, to end up with having and the background conditions and what's happening in the extratropics. That's another sort of influence on what's happening in the tropics, you might say. That gives you a development of an El Niño event, and how much it will grow or not also depends on a lot of these processes, and that's why they're still generally difficult to predict since the 80s, and also that's why models have challenges, because you need to get all these things right, and especially the clouds that Jessica also mentioned before. Cloud feedbacks are very important, so all of these come together.
But that chain reaction that makes an El Niño grow in a few months, warm up the Eastern Pacific, it's like, we call it the Viernes feedback. We just name it after Viernes. But our understanding of El Niño has changed since then. Then La Niña was identified or given a name in the 80s, and the community has worked on that and how they switch phases, how you go from an El Niño. My mom knows that after an El Niño, there's always a La Niña. Especially, I grew up in Argentina, where El Niño also has impacts on rain, so I remember all these El Niños. So you always know that after El Niño comes La Niña, but what we also discovered in the last 10 years, or not discover, but recognize that after La Niña, El Niño doesn't come. So it takes a few years until another big El Niño can happen, and predicting that interval is what is challenging, when the next big El Niño will happen. So there's a lot of research ongoing. People will be talking about that at today's session, about how El Niño and La Niña change phases. That's still an area of research. El Niño to La Niña is easy. La Niña to El Niño is really hard. But once El Niño is ongoing, we know that after 6 months, it's going to peak, usually around Christmas. That's why it's called El Niño. So we know all those things, we know for sure.
Right, many thanks to our panel. You can reach them one-on-one if you have more questions. We resume at 10 with to Etna, new results from 2 classic volcanoes.
Good morning and welcome to our 10 o'clock press conference. Et tu Etna, new insights on classical eruptions of Etna, Vesuvius, and Santorini. And today we have Morgan King from the College of St. Benedict and St. John's University, Rafael Castro from the University of California at Berkeley, and Krista Evans from the University of Hawaii at Manoa. I'm going to turn it over to Morgan to start us off.
The laser pointer, or so forward, back, laser pointer. Okay, great, thank you. Hi, everybody, thank you for being here. So I'm Dr. Morgan King, and I'll be talking to you a little bit about the historical perspective on this interdisciplinary project on the eruption of Etna in 44 BCE. So we're really interested in a series of years, 44 to 42 BCE, which were a pivotal moment in Roman history, in this sort of long, evolving process of the transition between the Republic and the Empire. And this time period also coincides with an underappreciated, abrupt, and dramatic climate change. Our hypothesis is that the cause of this climate change is an eruption at Etna in 44 BCE, which is attested to by many historical sources. In this project, we compare historical records, proxy records, and atmospheric models. I'm going to focus with you on the historical records. I work on Roman history and culture, so that's my area, but my colleague Rafael will go through the proxy records and atmospheric models in more detail with you. And as we look at this evidence, we're looking at sort of two attributes. One, do the location of the changes make sense for an eruption at Etna, and does the time of the changes make sense? So I'll give a little bit more context on the history here. So the end of the Republic is an incredibly tumultuous and complicated period of history. We could look potentially at a 100-year process, which involves multiple civil wars. This political upheaval, we believe, has partly obscured a really major climate disaster. We've got a timeline for you here outlining just basically the last 15 years of the Republic. And you can see we've already got 3 civil wars, multiple famines. And the period that we're looking at here is 44, which coincides with both the assassination of Caesar and this eruption of Etna. Environment played a really important role in Roman life, as it does today, right? And we can think about this in 2 major ways. One, we can think about symbolism, right? That Romans actually are going to interpret events in the world around them as having political and sort of cultural, religious import. So we can think of omens, divine favor, disfavor, etc. There are also really practical effects of the environment and climate, right? Disastrous weather can impact trade and the ability to travel. Famine, public health can all cause riots and political unrest as well. So to hone in even a little bit more closely on these years, a guy by the name of Julius Caesar in the 50s and 40s was consolidating power in Rome. The sort of pinnacle of this is in the beginning of 44 BCE, he declares himself dictator for life of the Roman Republic, basically institutionalizing one-man rule. This turns out to be a shorter tenure than he probably anticipated, as a couple of months later, he's assassinated by a group of senators led by a man named Brutus. His death leads to a power vacuum that results in several years of civil war, and eventually the rise of his heir, a man named Augustus, as the first emperor of Rome. I say all of this to give some context and also to make the argument that this is a really important time period for Roman history, for world history, also for literature and art. Everything from Shakespeare's Julius Caesar to the more recent HBO's Rome depict this time period and its events. Okay, a little bit of geographical context. So the Roman Republic at this time was quite diffuse. It went all the way from Spain to modern-day Turkey, Egypt. Well, Egypt was not technically a province yet, but was already sort of incorporated in a lot of the structures. a lot of the agriculture, a lot of the food that's feeding all of these provinces is coming from the east, from Egypt especially, but also modern-day Turkey. Worth noting, so Etna is in Sicily, which is right in the middle of this territory, right at the heart, and very close to Italy, where we're going to see a lot of effects. And we have eyewitness records of a major eruption at Etna shortly before the assassination of Caesar in 44 BCE. And in the immediate aftermath of Caesar's assassination, we hear a lot about climate effects. Some of these are associated with Etna by Romans, and some of them are not. But they're all compatible with the effects of a major volcanic eruption. So the first major one that Romans talk about is darkened skies. So apparently the day after Caesar is assassinated, the sky turns dark and the sun is blotted out. There are also, for several years, cold winters. There are famines in Egypt and Greece. And there are also solar effects. So famously, when Caesar's heir Augustus returns to Rome, people see a halo around the sun. And that's what the image on the right, the image on the right here, you can sort of see actually, so they also call this effect sundogs, because you can see sort of the two suns on either side, but it's also actually from a halo. And this was seen as being very significant. So there are political and sort of social ramifications of these effects that we see in the record. Romans interpret them as having meaning. And you can imagine, if you lived in the time period and the person who's completely in charge of Rome at this time is assassinated and then the sky turns black, that's going to feel meaningful. It's going to feel apocalyptic. And it was interpreted as a sign of divine disfavor. Likewise, when Augustus comes into Rome, that solar halo is interpreted as a sign of divine favor for him. And it gets worked into the mythology of how he is meant to end up the first emperor, how he's meant to take control and set things right. Oftentimes, so we hear a lot about these environmental effects in the context of sort of prodigies and weird things that are happening in this time period that are interpreted in this political way, which I think has also contributed to them being somewhat overlooked. But our research and our project suggests that actually, these, far from being sort of just propaganda, that these are sort of natural human responses to some really substantial climate change that's happening at the time. So ice core records show that one of the largest eruptions on record occurred in 44 BCE, and a major climate disaster lasting several years. You can see we've got this sort of scale here. So this would be what we have on the ice core records. So larger than anything that we've seen in the 20th century. One of the, I think, 3 largest that we have on record. So this raises the question, especially in the context of the ancient records of these environmental impacts. How did the environment change in 44 BCE? What are the impacts across the Mediterranean and even globally? And also, can we ascertain whether these changes might have been caused by this eruption at Mount Etna, which is so thoroughly recorded? And with that, I'll hand off to my colleague Raphael, who's going to present more of the science.
Cool. Thanks, Morgan. So you've seen this picture before, but just to explain a little bit more. The white smoke is steam, and then the black smoke is ash, and you can see it being moved kind of like up and to the right or up and to the left by the winds. And so that's pretty much what we're going to be looking at here. So a lot of those historical changes after the eruption are pretty similar to what we see after a modern day eruption. so if in this picture we have a cartoon of Etna erupting, and you have a lower part of the atmosphere and an upper part of the atmosphere, and that's going to be relevant in a second. So the eruption releases sulfur aerosols, and those aerosols actually do a lot of different things. So once they're up in the air, they're actually blocking the sun, and that's going to cause some temperature drops, but that's also going to cause the skies to be darker, which is like what we saw in the historical accounts. It's going to cause those sundogs. It's going to cause those temperature drops. It's going to do some agricultural damage, mostly because of the sunlight not being able to make it to the crops. And it's going to cause some health and societal effects. So we saw the historical effects. There's also some health effects. They can cause like respiratory diseases, as we'll see in a second. And like I said in the picture, most of the location of these aerosols is going to be determined by the wind at that time. So what we actually did was try to just make a good guesstimate for where these winds would take these aerosols. And obviously we don't have satellite data for 44 BCE, but we do have pretty good climate reanalysis data from like 1948 to present. So what we did was basically just run this atmospheric model for all those years, from 1948 to 2018, and just get a probability of where these volcanic aerosols would go, and then compare it to our proxy records that we have to see if they agree with each other. So this is the picture that we saw earlier. We have in green on the bottom more modern eruptions that are smaller. Even these small eruptions are causing pretty big impacts. They do an 8% drop in crop yields, which is pretty huge. We have an intermediate eruption, which is, it caused 142,000 respiratory deaths, which is huge. And then there's this mystery point in 44 BC that we're trying to explore here, which is significantly larger. And so we're trying to explore this sulfur anomaly that we see from this ice core record. So we're going to look at other records to get a good sense of what's happening. We see a drop in temperature here from these two records. And then here we have a crop yield record. It is a record of China, and we'll see in the model later on that these effects do go as far as China, and that's why we're seeing a crop yield drop. And then there's also a coin hoard record, which will give us a good sense of civil unrest. I think this is a very interesting record. It's archaeological, and you can imagine that back in the day, banks were maybe less common. And so what are you going to do when the skies are turning dark and there's a bunch of stuff happening around you? You're just going to bury your coins, and then you die of respiratory disease because of the ash in the air, and your coins stay there for us to dig up 2,000 years later. And so we can plot all these records on a map and just see like where the effects would be spatially. And we see most of these effects happening in the mid-latitudes, and so we can compare our model. And so here we see that most of these effects do in fact happen in the mid-latitudes. Here the colors are going to be the height of the particles, and we're just going to, the eruption is happening on February 15th, and we're just going to run the model for a few days, 2 weeks, just to see where things are going to go. So the main thing we're looking for is to see if the eruption is actually going to cause effects in Rome, which is where the eyewitness accounts are. And so we're going to be looking for the lower particles to be in that area, which we do see. And then for the upper atmosphere particles, we're going to try to make sure that those actually do make it all the way up to Greenland, where we're going to see these ice core records. And we're also going to see that they go all the way to China to be able to cause these crop yield failures. And so just to kind of recap, we want to see that the fall of the Roman Republic coincides with these climate changes, which it does, as we saw in those timelines. We hypothesize that it's because of this eruption in Etna. And to try to further this hypothesis, we're going to compare historical records, which Morgan talked about. We compared proxy records, which is what we saw with the ice core records, with the coin hoards, crop yields, and the sulfur records. And we're also going to look at the atmospheric models, which is these particle dispersions that we're looking at that are from modern day climate reanalysis data, but we're going to use it as just like an idea of what might have happened back then. And so basically what it comes down to is we're going to look at the location of the changes and the time of the changes to make sure that those coincide, which they did to a decent degree. So that's all I have for you all. Thank you.
All right, thank you. Oh. So Now, moving on to the precursory activity and cultural response comparison of the late Bronze Age Santorini, Greece, and AD 79 Vesuvius Plinian eruptions. So to give you a little background on the location, we have Santorini located in the southern Aegean Sea, approximately 120 kilometers north of Crete. Santorini is made of 5 islands: Theresia, Camini, Theresia, Esperanza, and Theresia are remnants of one larger island that was destroyed during the late Bronze Age. The reconstruction of this island is currently ongoing, so unfortunately I cannot show you that. Then about 1,500 kilometers east of Santorini, we have Vesuvius, located in the southern Campanian region of Italy. So to give a quick little timeline, we have the Santorini eruption, which was about 1650 BC. And the big thing to realize about this is that it is one of the largest eruptions that we've seen in the last 10,000 years. And I should also note that there have been no bodies found at the archaeological site of Akrotiri on Santorini. Then in AD 79, we have the Vesuvius eruption, which was a slightly smaller scale, and people were killed in place. So we have several different precursory activities that we use to determine volcanic eruptions, which is seismicity, ground deformation, and eruptions. So looking at Santorini earthquake history, between 1990 and 2019, approximately 79 earthquakes have been recorded. In 1956 was the last major earthquake that destroyed buildings on the island. And then we also have the archaeological record of Akrotiri that shows significant earthquake damage at the site. Then Vesuvius earthquake history, we have about 388 earthquakes that have been recorded between the years of 1985 and 2019. Luckily for this region though, we not only have the archaeological record, but we also have the written record. About 17 earthquakes have been recorded in the written record, with 4 of these also being seen in the archaeological record, including the AD 62 earthquake, which initiated the movement of magma and destroyed, had significant damage in both Pompeii and Herculaneum. So now let's move on to ground deformation, which we only see at Vesuvius. So it was used, the aqueduct system was used to model the ground deformation. As you can see with this blue line here, that is the original slope needed for the aqueduct system to have a proper fall. If there was any movement of the ground, this aqueduct system is going to break, and it is also seen at the archaeological site of Pompeii that this aqueduct system was being repaired at the time of the eruption. So now let's move on to volcanic eruptions, which we see at Santorini, but not precursory eruptions at Vesuvius. So at Santorini, there were 4 individual pulses of the precursory. This is very significant because the Therans on Santorini got away at this time. But then there was a short time gap that they came back and started sweeping everything up into a pile of debris. Then these people left again. So the big question is, where did these people go? Because there is no evidence of them moving into another island. There is no relic of Theron craft, Theron art, an influx of people at this time. So we know during the first phase of the Plinian eruption, it most likely created pumice rafts around the island. So they had gotten these boats and started paddling away in pumice rafts. So we have learned from Broodbank that they can paddle at about 1.7 kilometers per hour. Pause for dramatic effect. So after 8 hours, they have traveled 13.6 kilometers. This is assuming that they are paddling in pristine ocean conditions. So they are most likely not this far. So after 8 hours, this volcano, this eruption transitions into what we call phase 2, which is a series of pyroclastic density currents that are traveling in all different directions. Now, we know that pyroclastic density currents travel across water. We have seen this with the 1883 Krakatoa eruption, and we have most recently seen this with the 2019 Stromboli eruption. And using the information from the 1883 Krakatoa eruption, we can estimate that pyroclastic density currents can travel across the water at about 4.3 kilometers per minute. So after about 5 minutes, these people have been overwhelmed by pyroclastic density currents and have most likely been killed at sea. So again, we use earthquakes, deformation, ground deformation, and precursory eruptions in order to determine impending volcanic eruptions. While looking at Vesuvius and Santorini, the responses to these eruptions have been various. Whereas at Pompeii and Herculaneum, you see people trying to escape or trying to wait out the eruption and were killed. And at Akrotiri, these people abandoned the island, returned, and then abandoned the island again, but were most likely overwhelmed by the pyroclastic density currents at sea.
All right, thank you, Krista. I'm going to open the floor to questions from reporters in the audience.
Hi, Tom Garland House, freelance. I wonder if you could give us an idea of sort of the scale of the magnitude of the Etna eruption. I know you said it was sort of on a scale that we haven't seen historically, but is there any type of template, current template, like it was for Mount St. Helens or something like that?
Okay, I mean, we don't know, like, for sure exactly how big it is. The thing we're looking at that looks really massive is the sulfur spike. And so specifically for Etna, like, the tougher deposits weren't that much, right? So, you know, from the deposits that you would see from an eruption, you would imagine that it was like a relatively small eruption, but Etna is pretty gassy. And so, like, in that picture that I showed where there was gas coming out of the eruption, you see steam and you see ash, but what you don't see is like the carbon dioxide and the sulfur coming out of the eruption. That's just invisible gases that are going to travel up. And so it could have released a lot of sulfur, and you wouldn't really see that. So when I say like a big eruption, it wouldn't necessarily look huge and spectacular. It would just release a lot of sulfur like continuously. And that's that big spike that we're seeing that causes all these effects.
Thank you.
Mm-hmm.
Do you have other questions?
Christoph Seidler, Der Spiegel, that's on Etna again. Have the results been published, or how does that work?
The results have not been published yet, but I think will be soon.
you have other questions from the audience?
Horst Rademacher from Frankfurter Allgemeine Zeitung in Germany. Just a question about the precision of the dating of the sulfur spike in the Greenland record. I mean, you put it, I think you even put a date on it, 15 February or something like that. So how precise is that?
So the 15th February that we have is actually from the historical accounts. We don't know that the eruption happened right on February 15th, but actually, can I show a slide?
Sure.
So, I mean, we don't know if like a super high precision. Plus or minus a year, you said? Okay, so that the ice core is plus or minus a year. And then for February, like I said, it's the historical accounts.
Within a year.
Yeah, plus or minus a year. So, you know, it's not like we can't necessarily say it was 44, but we can say it's somewhere around there. And then for February, what we did was we ran the model for different months just to see where the scattering would go. And February was actually the month that agreed the most with where the records were, as you can see here. So this is just a distribution of where the particles would go. And you see this one going like off to the right and a lot in Europe, which is where the crop yield failures were. So that was the main reason we kind of put the timeline together, but it's still some uncertainty there.
Hi, I'm Tushar, who is part of the study. So I would also add that so there is about a plus minus 1 year uncertainty in the ice core records, but with variety of other records which show a large temperature signal that you should expect to see for that much sulfur release, because it's about 5 to 10 times the size of Krakatoa in 1883. If you start combining all those records, then you get a little bit more precision because they have different uncertainties. So that helps pin it down more closer to being in 44 BC time period. So the ice cores themselves have about plus minus 1 year of uncertainty. But when we start comparing the ice core records with the variety of other proxy records, a couple which Raphael showed, but we looked at a variety of other ones, they have their own uncertainty, but you can start to look at what is the likelihood that they all slightly offset and have different causes versus being around at the same time. So that gives a little bit more precision to suggest that it was 44 BC. But there are uncertainties with all the aging methods of about a year in general.
Do we have any more questions from the audience?
I'm curious about what historical records you consulted, because the fall of the Roman Empire, I think, was a pretty complex process that played out over a very long time.
Yeah.
So I wanted you to sort of clarify what you mean by that. You know, what are the evidence of damage to the empire that coincide with this event? I'm just trying to clarify that a bit.
Yes, and you know, we do want to be clear. The fall of the Republic is an incredibly complex time period, and you probably first have to look at political, military, economic causes for that. So we do not want to say that, overstate this, but that there is clear evidence of a climactic disaster in this time period, and that's probably a factor that we haven't been looking at closely enough. And that, in fact, our sources actually do reflect concern over climactic change and are interpreting it. And so we do have, we have evidence from contemporary poets. Virgil, Tibullus both write about it. But we also have some ancient historians, Livy, Plutarch, Suetonius, also all talk about it. And there are others. If you email me directly, I can give you more citations. But we are seeing it in a variety of written sources, as well as some of the archaeological evidence.
So is the coin hoard record new?
No. There is a citation.
Okay. Thank you.
Do we have any more questions from reporters in the room? Anyone on chat? Nope. All right, well, I'd like to thank our panelists. And that is all until 11. We will resume with the Arctic report card. Thank you all.